The first part of our motion unit that we talked about today. So I'll just kind of go through some of these speed, velocity, and acceleration problems. The first thing is I want to really quickly go through this one where we're just doing a little bit of dimensional analysis. Now this isn't really speed or velocity, but I want you to get in the habit of doing this. And I'll tell you the reason is because sometimes when you're doing problems, you can figure out the answer to it, even if you don't know the equation. If you kind of realize, if they tell you what they want the units to be in, they kind of a clue as to how to solve the problems. So in this case, we have a car traveling at 100 kilometers an hour and we want to turn it into meters per second. And so always what I'll do in this case is I'll put out what I want on the left, in this case, or I'm sorry, what I have on the left. In this case, I have 100 kilometers in 1 hour. And what I want is meters per second. And so I'll just put meters per second over here, just to kind of give myself a place to focus on. And then I just immediately start getting rid of units that I don't want. So I have kilometers, I don't want that. So I'm gonna put that on the bottom of a fraction bar, because this means that kilometers divided by kilometers, this causes it to go away, and it's now 1 and it's gone. So now I have to go and start hunting for conversions. And so I'm going to say, well, what can I do that might turn kilometers into meters? And that's an easy one, right? Because we know that inside of 1 kilometer, there is 1,000 meters. And so this has gotten rid of my kilometers and it's left me with meters, which is what I want here on top. So at that point, I've got this top part taken care of. Now I have this hours, and I want to get that turned into seconds. So I want to get rid of hours. So I'll do just what I did with kilometers. Instead of putting it down here, I'm going to put it up here. So I have hours right here, 1 hour. And I'm going to use a conversion factor of minutes. You could use seconds, but most people don't keep track of how many seconds are in an hour. And there's 60 seconds, or 60 minutes in 1 hour. And I'm close, but I still have to get rid of the minutes and turn it into seconds. So I'll just do exactly what I just did. Just move the minutes on top and put seconds down here. And now, if you look at this, I've gotten hours, it's gone away, minutes has gone away, and I'm left with seconds, which means that I have this equation pretty much solved, other than putting in 60 over or under 1 there. And then I just multiply across, divide by whatever is on the bottom, and I think that's just 100 times 1,000, which is 100,000 divided by 3,600 gives me 27.8 meters per second. Okay, I'm going to skip this problem since it's the same thing. Okay, so let's talk a little bit about, this is our opening shot at motion. And so this is a pretty classic physics question, and it's kind of designed to trip students up a little bit, but it should make you aware of how to do everything going forward. So what we're looking for velocity and speed, which is what we're looking here, we're looking for distance for the speed, distance, and we're looking for displacement for the velocity, okay? And so that's an easy concept in a way. If you think about distance, it's just the total length of the journey. So if you decide you want to go from, say, Los Angeles to New York, and you decide you're going to go, instead of going west, or rather than going east to New York, you take a plane, you fly from Los Angeles to New York, you could theoretically go around this way, right? You could circle the globe going in the westerly direction and just kind of around the entire globe, and you can end up in New York. So you've gone much, much, much farther, and so your distance would be much greater. But displacement would be the same if you went from Los Angeles to New York this way, or Los Angeles to New York around the other way. So you might go, say, 22,000 miles if you went from Los Angeles and flew over the Pacific Ocean and went around the Earth, as opposed to maybe going 3,000 miles if you just flew straight across country. Doesn't matter, displacement is the same because it's just from point LA to point NY, right? So it doesn't matter if I went this way or not. Okay, where's distance does. All right, so let's calculate this. I've got a circle, perfectly circular track. A runner circles the track in 88 seconds. I want to calculate the average speed of the runner. Speed is equal to meters per second, so I'm going to take 400 meters. I'm going to divide that by 88, and I get a number of 4.4 or 4.55. 4.55 meters per second. Okay, now displacement. This is a tricky one, and this is the reason why this is a classic physics question, and it's always kind of the opening gambit there for physics, because it's kind of designed to trip you up, because since it's meters per second, it kind of is this, looks like it should be the same, but the reality is that the displacement is 0. So this runner circled around like this. They started at the starting line, they circled around, ended up at the same spot. Displacement is 0. So the answer is average displacement, 0 over whatever, who cares? The average velocity is 0, okay? Instantaneous velocity of the runner after 44 seconds. Now this one is kind of a weird question. We can actually solve this. Normally with instantaneous velocity, you need some sort of a graph, or you need to be able to measure like a photo gate, you know, a real small increment right here. But this is telling us that this is going at a constant speed. So if it's going at a constant speed, then it must be going at a constant velocity. Now I said up here that it was 0 for circling, but it's not 0 at 44 seconds, because the constant speed was 88 seconds. That means it's made it around halfway, the runner has, and so we can actually calculate that. So there is velocity here, it just isn't any velocity when it reaches back to 0. And so we're going to use some geometry here. We're going to use one of our favorite little equations, which is the diameter of a circle is equal to the circumference divided by pi. Okay, and we know the circumference is 400, so 400 divided by pi is equal to 127.3 meters. So our displacement is 127.3. And then we can figure out what the instantaneous velocity, or let's start with saying we're just going to figure out what the velocity is, and then we'll talk about why we can figure out instantaneous in this case. So if I have a displacement of 127.3, I can divide that by 44. And I get a velocity of 2.89 meters per second. Okay, and the reason that this case we can say it's instantaneous is because of this word right up here. Constant, okay? Constant means it's that we know it's going that speed the entire way around. So it's also going that velocity the entire way around. So, you know, we can say that this particular case is instantaneous, even though normally it doesn't work. Okay, now, this one here is one of the problem where I want you to get in the habit of starting to use drawings whenever you're doing physics. It's going to be very helpful if you can do that. And so we have this little diagram we're going to make, and we're going to try to figure out the speed. And I think we'll just keep the speed as kilometers per hour. It kind of makes it a little easier. So what is the speed of a car that travels 10 kilometers north? We'll say 10. And then 40 kilometers east, and then turns and travels 20 kilometers south in 1 hour. Well, this is simple enough. We can just add this, right? 40 plus 20 plus 10, 40, 50, 60, 70 kilometers, 1 hour. So 70 kilometers per hour. But with velocity, I don't care about all this distance here that we were traveling. I'm only interested in this. You know, this point right here, right? So I want to know the distance between here and here. So for this, I'm going to use our trusty Pythagorean theorem, and I'm going to solve for the hypotenuse here. And so we know that on this side here of this triangle is 40 kilometers. And in this side, because this distance was 10 and this was 20, we know this is 10. And so I can get my answer to this by saying 40 squared plus 10 squared is equal to if I square it, is going to be equal to my displacement. Okay, so 40 squared plus 10 squared, and then square root thereof, is equal to 41.23 kilometers, which is how far we traveled in 1 hour. So there's our answer.